Chemical Engineering 757, Polymer Rheology, H.H. Winter, Lecture 9A. The extensional flow behavior is very important for processing. Very often the shear information is not enough. Materials might look very similar in shear, but process very differently in fiber spinning, blow molding, or film blowing, for instance. So we should look at extensional rheometry. Now, the general definition of an extensional flow is simply the vorticity of the velocity is equal to 0. That's the definition of extensional flow. And as a consequence of that, we need a velocity which is described by the gradient of a scalar potential, phi, and this scalar potential, phi, could be a position of x, and actually it could be a function of time also for transient extensional flows. So that's the characteristic, that's the fingerprint of extensional flows in general. But for rheometers, we would like to have something more. We want to have extensional flow where the rate of stretching is uniform throughout the sample. So we would like to know what's the kinematics for homogeneous extensional flow. And you could do this as an exercise. Find the potential function, the scalar potential function, which gives uniform stretching throughout the sample. And if you do that, you will find that the velocity field is given by the components. Take the extension rate in one direction, which still could be time dependent. You know, the extension rate could be uniform throughout the sample, but it could be a startup or a stopping of flow and relaxation. We just require that it's uniform. So extension rate in one direction times x1, the extension rate in two direction times x2, and the extension rate in three direction times x3. Those are the three components of the velocity vector, and those are the components in the principal coordinate system. That's the coordinate system which makes the stress tensor diagonal. And in extensional flow, we have the luxury of choosing a global coordinate system which has that property. The entire flow can be described in this principal coordinate system, which simplifies everything. Now, the constant density I wanted to mention. So for constant density, the sum of the extension rates, epsilon dot 1, epsilon dot 2, and epsilon dot 3 is equal to 0, which is nothing else than the expression that the divergence of the velocity field is equal to 0. So that's the constant density requirement. And then we would like to know the position of a material element in the extensional flow at different times. So position. And if this material element is, say, at some initial time t0, we have the position x1, 0, x2, 0, and x3, 0. This would be the material element at some position in the flow field. Then at some later time t, the position, say, would be given as x1 as a function of time now at this new time, and that's given as the position x1 at t0 times the exponent of an integral here over the extension rate in one direction at some intermediate times integrated from, say, T0 to T, and you would calculate the position of the x2 position, x3 position in the same way, in the same fashion. So that's the kinematics which we would be looking for in an extensional rheometer to produce the uniform extension rate throughout our sample. The motion is given by a flow field, which I have here. If you use the figure here, we can define a stream surface which is given by material elements moving along a path like this. Initially, we would take material elements sitting on an ellipse like this, and as all those material elements move down in time, they would describe a circle, and sometime later, they would describe an ellipse stretched in the other direction. That's the most general format of the kinematics. I wrote down the equation down here, a material element sitting at x0 initially, and on this ellipse here would be sitting at this type of ellipse at some later time. And the parameter is really the ratio of the extension in y direction versus the extension rate in z direction. This is this parameter A, which is on the top. So that's the most general type of homogeneous extensional flow which we would like to produce in a rheometer. We can look at special cases. We could, for instance, take uniaxial extension, where a circular material element, as it moves down in this direction, will always be circular, but it just increases its diameter, and say a little cylinder up here is being squished down, and it will be a disc down here. If it goes downwards, or if it goes upward, a little disc down here is being stretched into a fiber. So fiber producing of this way would be uniaxial extension with a positive extension rate, and equibiaxial extension, making a sheet, making a little flat disc out of a fiber, is a uniaxial extension with a negative extension rate. But all of this is an axisymmetric flow. Typically, you would need different rheometers to stretch in positive or negative direction. It's not as easily reversed as shear flow, where you could go backwards or forward. Another popular extensional flow would be planar extension, where material elements move around hyperbolical surfaces. Entrance would be on the top and on the bottom, and the material would be leaving on this side and that side. In all of those cases, the material element at the center is not moving. That's a so-called stagnation point, and in planar extension, it's really a line. It's a stagnation line of zero velocity. The material element there is always sitting at this position, and we can observe it. It's still being stretched. So zero motion doesn't mean zero deformation. The motion is zero, but it's being stretched over a long time. And in fact, we can put windows on this side and on the back side, and then observe changes in the material by some optical techniques. And that's very popular. Keller, for instance, in Bristol looked at polymer solutions, stretch coil transitions in polymer solutions by exactly this technique. Or we built a die like this. I brought a little rusty piece. It's about 5 years back that Katsaros did extensional flow experiments with that. And I opened it up. We would feed a polymer blend in here and on this side, so there would be a symmetric flow. And as these two streams approach, they have to slow down, and the elements are stretched to the side. So there's an exit here and an exit on the other side. You're producing extensional flow, have a window across, and then have very nice possibility of observing phase transitions due to extensional flow. And it's a beautiful experiment, because see some critical phenomena, some opalescence, some beautiful colors coming in. So it's a powerful technique to modify the material and utilize the stagnation point in the center. The kinematics associated with extensional flow is exactly the kinematics which we discussed initially. So just want to remind you that we have all the tools available. The stress is in diagonal form because we have this luxury of choosing the principal coordinate system as a global coordinate system. The pressure or the stress difference between 1, 1 and 2, 2 or 2, 2 and 3, 3 is driving the flow. So if all three components are equal, then there's no extensional flow, would be hydrostatic pressure, and nothing would be happening. Therefore, in extensional flow, we always say pull in one direction. On a rod, for instance, we have P11 being tension, and those two would be 0 or would be ambient. And that difference between P11 and Pi11, Pi22, it gives us the, introduces the flow in the specific experiment. The material functions which describe the flow then would be the stress divided by the strain, but by the strain rate, there would be a viscosity. And note that we put the first normal stress difference divided by the extension rate and the second normal stress difference divided by the extension rate. The third extension rate is not a free variable because of conservation of mass and constant density. So that's already prescribed. Now, if you don't talk about a liquid where you would look at viscosity, if you talk about a solid, you would divide the strain, the stress here with the appropriate strain, and from constitutive equations you will see that a strain difference will come out of the calculations, and the same you could do for the 2, 2 minus 3, 3 component. In a step strain experiment, you also would use this type of material function. It would be a time-dependent modulus, which you would be measuring, which you would define then in extensional flow in that fashion. So it looks a little bit different in extension than in shear. The actual rheometer is not so easy to build. There's a wish list now which I want to discuss with you. What would we like to have what would be the ideal extensional rheometer? Certainly we would like to produce this irrotational flow as defined on the blackboard, and we would like to have uniform strain rates, would like to have that, have a homogeneous extensional flow. Could be time dependent, but homogeneous. We would like to apply large strains because the molecular changes are most visible as the extensions are very, very large. Also in polymer processing, the stretches are normally very, very large. So we would like to verify this. And for a material element sitting at the stagnation point in our kinematics, we can achieve large strains because just sitting there and we are stretching, and we can just go forever. In, of course, continuity, the continuum assumption tells us that's always the same material in there. Diffusion will set it in, and so on molecular scale, some changes will arise if you really stretch to large values. Now, we would like to measure the strain, and we would like to measure the stress, and it's all done, right? We are in business. Now, how can this be verified? What are the current methods of producing extensional flows? I divided them into two types: the batch systems, which are really systems where a small sample is used in the extensional flow experiment, versus the flow systems where a large amount is, say, pumped through our rheometer. So it's actually nice to have a batch system, but it has also its limitations, as you will see. Now, in our rheometer, we either produce uniaxial extension. We have to make up our mind what type of rheometry we would like to do. Or we go biaxial, and if it's the same stretching in two directions, it would be equibiaxial. Or it would be planar extension, which we could produce. Now, uniaxial is very popular. Let me Here I brought, for the batch systems, I even brought some cartoons here just to remind you. So this is the uniaxial extension. If we go in positive, if we stretch this fiber, if we make it longer, call it elongation or uniaxial extension. Or if we push this fiber, make it smaller, we're kind of making a disc. Or we could grab even a sheet and stretch it uniformly in all directions. That's called equibiaxial extension. So both of them would fall into the uniaxial extension category because it's axisymmetric. And then there's the planar extension geometry where we take a little cube and somehow grab it and pull it. It goes down in this direction while we keep the third direction, the width of that material element, constant during that deformation. Now a simple way of producing uniaxial extension has been proposed by Coxwell in 68, and Münstedt built a nice apparatus, pushed it further in 75 when new drive units appeared. It goes something like this. A little sample, a cylindrical sample down here, is attached to a rod, and this rod is driven at a velocity which has to increase exponentially to generate uniaxial extensional flow at a constant rate. Okay, so this is driven at a constant, and down here we measure the force. Now this part I blew up here just to describe that a little further. See, this is our little sample. It's glued onto the surface. You would have to produce the cylinder first, equilibrate it so that all the structure is relaxed. All previous stresses have disappeared. And then you have to find the suitable glue which connects your polymer, your sample, with the metal surface, and that sometimes is a hindrance, but it can be done. You use some cross-linking polymer, for instance, or super glue. And then you stretch this sample here with a rod. This goes in this direction. Initial length is L0, and the final length, the maximum length, is given by the length of your bath. There's a strain limitation coming in. The stress is measured by the amount of deflection of the spring. So the lower part of the sample is mounted to a little spring, and with an LVDT you just measure the deflection and you get the stress. All of this is submerged in a heating bath because you would like to measure at high temperatures, like polyethylene at 180 or 200 degrees C, like in a real film blowing experiment, for instance. So you want to have the real operating conditions. So you use hot oil, and that sometimes causes a problem because the oil might go into the sample, and you would be swelling your sample and change the properties of the material. So you have to be careful about this. A very nice experiment has been proposed by Meissner, and in 71 he had a famous publication on that. He simply took a long rod type sample and floated it on top of an oil bath. So the heating comes from the oil bath itself, and he grabs the sample now with pairs of rollers on this side and also on the other side, and those rollers move sample always away out of your test section in both directions. You always have new positions of grabbing while this experiment is going on. The diameter of this sample here is decreasing, is shrinking as the stretching goes on, as the fiber gets smaller and smaller. So the rolls have to accommodate that. They have to move closer together during this grabbing. The kinematics of constant extension rate, is achieved by making the speed of the rollers constant, by choosing a constant speed of rotation for these rollers and those rollers. The speeds don't have to be equal. Normally this speed is very slow and this is high, but just make sure that new material is being grabbed all the time. And at the end of the experiment, Meissner cut the sample here at about 8 places and collected the samples after this cutting, and that told him whether the sample was uniformly stretched. He doesn't want to have any nicking throughout. And whenever the weight distribution between those different samples is uniform enough, then he uses the data, he accepts the data. Otherwise, he would have to redo the experiment. The temperature has to be very uniform. Imagine you have a hot spot somewhere in the middle, then the sample would be stretching out in the middle, and everything would be could not be analyzed. The data could be not processed anymore. Polystyrene, for instance, has a much higher coefficient of temperature than polyethylene. So depending what polymer you're using, you have to be more careful with heating bath. So that's one reason why most data reported are on polyethylene and not on polystyrene. You might be wondering why this comes about. So there are simple reasons like that. So far about the strain. The stress is measured by the bending of this spring here. This drive is supported on the spring and an LVDT. So the data of which he got are very nice. I showed some of. Oh, where did we have those? Here, this is a typical data set. The material function, the first normal stress difference divided by the extension rate as a function of time during the startup experiment. The stress is increasing in time. Now, by dividing with the extension rate, all the data fall together coincide with the viscosity, and at some instant, at some time, there's a deviation where somehow the stress grows extensively. Okay, so those data are taken on melts. It is somehow necessary that the sample is fairly stiff so that you can grab the sample and stretch it. Now, recently, experiments have been done on dilute systems, on just polymer solutions, coming back to this method of Coxwell and Münstedt. I just want to talk all about the melt sample in the beginning. But for low viscous materials, this method of Coxwell and Münstedt, where a sample was put between two little discs, could be applied to polymer solutions. It's a proposal by Matta and Titus, and the data I'm going to show is really by Sridhar and Gupta and co-workers. So there are little Teflon discs. The oil or the polymer solution is caught in between the two. It's like a little droplet, and then those little discs are separated in time. You can see the inhomogeneity of the strain is really limited close to the clamp, but the fiber which is produced is nicely uniform. The extension rate, again, is given by the change of length in time and by using a suitable drive, which is easy in a commercial tension experiment. So we could choose that constant. The force would be measured by putting a little force transducer in a tensile testing machine, conventional tensile testing machine. And then we would calculate the stress as the force divided by the instantaneous cross-sectional area. The decrease of the radius is exponentially because of the type of kinematics. And Sridhar plotted some data versus time. You could see a very nice development of the radius. And the transient viscosity is very similar to the viscosity measured on melts. I drew a line through one set of points here. This is extension rate of 0.76. It seems to level off for the viscosity, and then there's an upturn as you saw in the polymer melt. And I think it's a neat device to measure extension viscosity of a polymer solution, which is hard to grab, but in that type of configuration, it seems to be possible. Okay. Now, the biaxial extension has been approached by Meissner in the same fashion as he approached the uniaxial extension. In uniaxial extension, he had a cylindrical rod, and then he just grabbed this rod by his rotary clamps and and to pushed material to the outside. Now, in this device, he takes a disc-shaped sample. It's about 5 millimeter thick, so it's a fairly large sample. It has about the size of a pizza. So sometimes we talk about this as a pizza stretching device. So it's stretching this fairly large sample, and Meissner put marks on the sample, so you could see how those marks have been stretched as the extensional flow goes on, and he could prove that the deformation is very homogeneous throughout the sample. The sample is cut here at the sides because somehow with a circular geometry, you have to get rid of the material which is pushed to the outside. A nice feature of this type of geometry is also that you could arrange those not just in a circle but in an ellipse, or you could go extreme and have 3 pulling on this side of a sheet and 2 in this way and down here. So you could produce extensions everywhere between axisymmetric case, this would be actually biaxial extension, and planar extension, where you just hold in one direction and pull in the other. So you can get data at intermediate rates. This experiment is limited to room temperature. You can imagine that you cannot heat this device to 300 degrees C. It would disappear. It would be a pity to do this with this device. But you can study polymeric systems at room temperature. If you remember this bouncing putty, for instance, some polymeric systems which have the interesting viscoelastic properties at room temperatures, and you can test those in this device. Now, we had some fun also with biaxial extension, and our approach was the following. We said to produce biaxial extension, we would squish a sample between 2 approaching plates. So this is a sample also maybe 5 millimeters high in the beginning, but the surfaces here are lubricated with a liquid which has a viscosity about 500 to 1,000 times less than the viscosity of the sample. So the stress transferred on this surface is mostly normal stress. The shear stress is negligible compared to the normal stress. So at this surface, we only have normal stress, and we could say this is a principal surface. It's a surface where the traction is normal. And we are squishing our sample from an initial radius to an intermediate radius drawn here, and we measure the height change, h0 to h, and by conservation of mass, we get all the changing geometry. The velocity field is given by the approaching velocity of the plates, and we can choose now an exponential function for this kinematics and introduce constant extension rate. So the extension rate is defined as the change of height as a function of time divided by the instantaneous height. And since the lubricant layer is very, very thin, we don't have to subtract lubricant layers. It turned out that we can just take the height by itself. And the normal stress would be measured now by measuring the force and dividing it with the instantaneous cross-sectional area of our sample. Now, this approach has the advantage that we use a very small sample. So this is the candy type experiment in comparison to the pizza. And it has the advantage that everything is contained in a small area, and we can go to high temperature. So in fact, this device was the first one which gave information on biaxial extension of polyethylene or polystyrene at high temperatures. We also used that device for stretching a liquid crystal material, a Vectra, which has a melting point close to 300 degrees C. No problem. You just lubricate your sample and you squish it and do everything you want to at every temperature. The difficulty or the limitation of this device is the loss of lubricant. After having introduced a certain strain, the lubricant layer gets so thin that you lose the effect of lubrication, and then there are deviations. So with this device, it's not so easy to achieve constant extension rates. But the advice is very nice for introducing a step strain experiment. Remember, we looked at step strain data of Osaki's group in shear and found that very informative doing step strain at various shear strains, going from the linear behavior to large strain behavior. Now, with this device, we could do step strain at high temperatures and at large deformations, and then get the equivalent function, the complementary functions to the step strain and shear data. So that's very helpful. If you would take this type of geometry here, the rotary clamp, and would try to introduce a step strain, then you would break the sample. You would just rip it apart very quickly. While, the difference concerning the stress level is that you're pulling on the surrounding, and the top and the bottom is at ambient pressure. So you're pulling, you have tension and ambient here, while here we are pushing on the bottom and the top, and we have ambient on the side. So the experiments are done at a somewhat higher average pressure level, but otherwise everything is the same. But this containing helps helps stabilizing the experiment at high rates. An experiment to produce equibiaxial extension is also the bubble blowing, and I assume most of you did that. Forming a bubble, forming a sheet of chewing gum in your mouth, clamping it with your lips, and then blowing against that. That's also equibiaxial extension. People have used that to produce equibiaxial extension in a real apparatus. Denson at Delaware and Dealey at McGill University. You have to drive this bubble blowing experiment at a certain rate to, you have to supply air in the correct rate so that your extension rate is constant. And then it's hard to measure the pressure under those conditions. And the overall strain is also limited because very soon the strain is different and the clamping than in the rest of your bubble. So it's hard to generate uniform stretching in this experiment. So the stretching between two surfaces is easier to perform. So the lubricated squeezing, in summary, requires a small sample. We can apply all kinds of temperatures which we would like to, which we need for our sample. Step strain is easy to produce, and the experiment is fairly easy. And it's kind of embarrassing that with a simple experiment like that, we get data which are complementary to the rotary clamp data of Meissner with a real elaborate device. Right? It's a beautiful experiment which Meissner built up, and he really can look at his sample. In fact, Zorsky also put glass plates in our squeezing apparatus and put marks in the sample, and then doing this lubricated squeezing, he also could look at the stretching and found also very homogeneous deformations there. Now the limitation of the lubricated squeezing is that the strain is cannot be too large because you lose lubricant. You change the kinematics. So far about the batch experiments in uniaxial extension, in equibiaxial extension. You could do planar extension also with lubricated squeezing by having the sample in a channel and containing your sample on the sides. That has been done by Larsen and Kahn and gives very nice data on planar extension. We also tried that for preparing some samples. So all of this is batch. Now how about flow systems? We would like to study extensional flow in continuous flows, pumping liquid, say, through an extensional rheometer. And the devices to use would be a converging flow, where the velocity is changing, is increasing in flow direction, or spinning device, where you grab a liquid and increase its velocity. In the 30s, Taylor proposed the four-roller apparatus. It just basically has he has four rollers which go jointly here so that they push liquid out here and this other pair pushes liquid out there. So flow comes in from both sides here. We generate a stagnation point, stretching in the center, and the possibilities of observing the stretching of a droplet is very nice. So that's very popular for polymer solution. But now realize that the kinematics introduced by those rollers is not equal to the ideal kinematics which I had out here on the blackboard. There are deviations. There's a constant velocity surface, obviously, while the velocity along a stream surface should be very high, should be slowing down, and then should be increasing again. So there are deviations, and the ideal stretching behavior is only produced in the immediate vicinity of that stagnation point. Now we could use a spinning experiment also to produce the right kinematics, but to produce now the stagnation point, actually this is an extra picture which is just for your enjoyment here. It's a spinning not from a die. We would supply liquid from a hoop type device here. We would supply spinning fluid here and then spin in two directions. That's the type of kinematics which we would need to satisfy, again, the kinematics out on the blackboard. That's the velocity field which is desirable to have. So the spinning should go in two directions, and nobody is spinning like that. So but just for you to appreciate the kinematics which we are looking for extensional flow. So we would be spinning in two directions. How about flow into a contraction? We built a die where we injected fluid on one side. Here, this is our sample fluid. And this sample fluid then is accelerated as it moves through the converging die. We wanted to get rid of the shear stress near the wall, so we entered lubricant on the side. So take off the shear stresses there, hopefully having plug flow in the center and some shearing, and shearing only in the lubricant. This is what we were attempting. It has several limitations. So let me go through that piece by piece. It's actually very, it's an experiment which is easy to do, but it has all kinds of problems. You saw a picture of that early on when we talked about kinematics. This is the converging die section of the schematic, which you saw before. So liquid is moving downward and it's accelerating as the diameter is decreasing. We have a wire across here which has some bare spots, and then by putting current, occasionally put a pulse of current in there, we produce bursts of bubbles which have some rectangular format here, and as these bubbles move down with the acceleration, this burst is being stretched longer and longer. But you also can see that the flow in the center is not perfectly flat. It's not just plug flow. There is still some shearing motion, and there is an acceleration. So in that sense, you immediately see plug flow is not being reached, and there's certainly shear in our liquid. And then we measured the pressure distribution on the side, which is also, in some cases, it was determined by the lubricant liquid which we entered on the side. So it's somewhat tricky. But the main difficulties are different. It's even more serious. The deviation. Let's compare the flow which we had with the idea of extensional flow which we would like to achieve. Now, this is the kinematics which comes out of the equation on the blackboard. This is the equation for constant extension rate throughout the liquid, and that requires a stagnation point in the center and entering fluids from the side and flowing up and downwards, like spinning in two directions. We should not just push liquid down here and have it converge, and we should have liquid coming in from the side and have flow up and have flow down to achieve the right kinematics. Van Aken and Janicic-Krieger performed an experiment like that, and they got actually reasonable data on uniaxial extension by doing this. So the feed should come from the side. And a material element, now I drew some element in here, could be a disk here, and as it moves, this disk moves down, it is gradually transformed into a fiber. This would be uniaxial extension. Or if the flow goes backward, the fiber is transformed into a disk and leaves on both sides, and that would be equibiaxial extension, depending on forward and backward. So that's the first problem. Our general setup is not suitable for producing the right kinematics, which we wrote down, which we defined in the beginning. Second problem. The surface and fiber spinning, or so, well, I actually should use, if this is our geometry here, if we come back to, yeah, this is our geometry, let's look at a curved surface like that. This is the curved surface here in our coordinate system Rx. Okay? Now, on a curved surface like that, we would like to know what's the stress. And the best thing we can do in the experiment is really lubricating the surface. That would mean we take off the shear stress and just have a normal stress on that surface. And the question is that admissible? Is that desirable? Now look at this. If we take a stress tensor, this defined like this would be the stress driving our perfect extensional flow. Now if we take this stress tensor and calculate the traction on a surface like this, by just take the normal on that surface, multiply it with this stress tensor there. This is the normal, by the way. This is the equation of the normal on the surface. Then we find that the traction has components in normal direction, and it also has traction in a shear direction. So the result is kind of obvious. Whenever you have a surface which is not a principal surface, you have a traction vector which has a shear component and a normal component. So in the extensional flow, we really should have a surface which is not lubricated, but a surface which is driving the flow. There should be some pushing in flow direction to generate the desired stress. So even if we have perfect lubrication, we will not have the right stress situation on the surface. Compare that to the lubricated squeezing. There we lubricated a surface, the top and the bottom of our sample, and those surfaces were principal surfaces, and we lubricated the right surface. But if you lubricate a surface in an angle, you're not achieving the stress situation which you really need in extensional flow. So even in fiber spinning, when you have a fiber converging in diameter, getting smaller, and on that surface you only have a normal stress, that boundary condition is not the perfect boundary condition for achieving uniaxial extension, for achieving homogeneous uniaxial extension. You actually should have some shearing on that surface to have the ideal geometry. Okay? So those are some interesting details on on flow devices. Problems with the flow devices are just surmounting. The initial or entrance conditions are problematic. See, when you pump liquid into the die, it has been exposed to some squishing and shearing and all this, and it will memorize that. So shear flow will be affected by that. Boundary conditions will be not satisfied because of the curvature effect and on the boundary not being equal to a principal plane, so there are deviations. There might be gradients in the extension rate. Flow instabilities, I haven't even mentioned those, but when your rates get higher, you will introduce some instabilities. The shear, there will be some shear introduced in the, with the boundary conditions. I mentioned this die here. Yeah, we built this die, and obviously near the wall there were tremendous errors due to the shearing. Only in the center region we achieved the extensional flow which we were looking for. Small strain is, well, it depends. When you're at the stagnation point, the strain is really very, very large you can produce in your system. So the conclusion is that the extensional rheology is a very sensitive measure for changes in molecular structure. So we really would like to have extensional rheometers available in larger, in a bigger variety and easy to handle, but it's still difficult. Very few data are available on well-characterized polymers, and you probably know why now. The interpretation of transient data is difficult. Well, if you have a clean experiment, that should be okay, should not be too difficult. Now, the batch method is advantageous for small samples, and it works very nicely in uniaxial extension for high viscous samples, and the newer data also for the low viscous samples. Planar and biaxial extension can be performed experiments. That's okay. And the flow methods, stagnation flow is very powerful for looking at samples, and spinning experiments are nice. So also flow into contraction is used sometimes to extract some information on extensional flow. For instance, the data you get in a capillary rheometer, after having done the Bagley correction and separating into a shear contribution and in this entrance pressure loss. Now, this entrance pressure loss gives some information on the stretching in the entrance region. And this is where it comes in. So it's somehow related to extensional flow, but in a complicated fashion. So that also would be a flow method, a flow approach for getting information on extensional flow. That's all I wanted to mention on extensional flow. Let's move to a new subject. So let's take a break. So it's a fun experience. Amherst, Chemical Engineering, Polymer Science, 757, Polymer Rheology, H.H. Winter, Lecture 9B. We are moving to a new subject, and that's linear viscoelasticity. We would like to characterize the material at small strains at first, and then at large strains. And it turns out that specific techniques are needed for linear viscoelasticity, and lots of information is already gained at small strains. And we should capture all of this in the beginning and then move on to the constitutive equations for large deformations. So the objective here would be to formulate a constitutive equation for small strain. But as you will see, there's a restriction, or actually it's an extension of that. It's only small strain as long as it is memorized. small memorized strain. So a material might be exposed to large deformation, but if it has a memory which is very short, then it only memorizes that very small deformation, and it can be treated as a linear viscoelastic material. An example of such a linear viscoelastic material is the Newtonian liquid. So if you look at the Newtonian liquid, where the stress at some time t is given by the viscosity times 2 times the instantaneous rate of deformation. That's a linear equation, and the behavior is linear even at large deformations. So that's one limiting equation for our linear viscoelastic model, which we are going to look for. And the other limiting case is the Hookean solid, which would be described by a stress which is proportional to the strain. The coefficient of proportionality is the constant modulus, and this is multiplied with, say, a strain between some stress-free state and the instantaneous state, and this strain could be defined as an integral over the rate of deformation tensor over the past from the stress-free state to the current state. So something like this. I had to introduce a small strain measure here when looking at the rate of deformation tensor. Later on, we will, of course, replace this with the finger tensor or Cauchy tensor and then go to large deformations. But these will be limiting cases for our constitutive equations, which we have to derive. Now, I will derive this equation, which we will call the Boltzmann equation. It's based on Boltzmann's linear superposition principle. I will derive that with a phenomenological approach. Remember, we looked at a material in a shear strain. This is our little material element exposed to shear strain, which is given by the tangent of this angle, and the response, the material function, was just the relaxation modulus. The shear stress was proportional to the shear strain, and the coefficient was this relaxation modulus. And this relaxation modulus for viscoelastic liquid was a decaying function in time. We talked about this when looking at material functions. So let's use that here for a moment, and let's look at the step strain. This is the information which we have available. We look at a linear viscoelastic material, and the stress after a single step deformation, the strain is 0, and then at time t1 we deform this material by delta gamma, and the response now we know is equal to, the response being the stress, is equal to the relaxation modulus times the strain. And the relaxation modulus is written as T minus T1. In our previous derivation, the deformation was introduced at T equals 0. Now we introduce the deformation at T equal 1, and the relaxation phenomenon, the relaxation process, starts at T1. So we look at the relaxation modulus at some later time minus the time where the strain was introduced into this material. That's the old information which was available. And now comes the linear superposition. We would take a material which is exposed to a sequence of strains, here delta gamma 1, delta gamma 2, delta gamma 3, at 3 different times. And the stress after this first deformation would be relaxing in this fashion and would continue relaxing if we wouldn't put in another strain. And again, the stress is relaxing. And then with the next strain, we again build up the stress, and it's relaxing like that. With the linear superposition, we would say the total stress is given as the superposition of all those stress responses. That's allowed at small strains, where everything is linear, the relations are linear. So the total stress is given as the sum of the individual strains multiplied with the moduli. And now note that each of the moduli starts to count at t minus ti, ti being the time where this little strain is introduced. Okay? Now, this stress here equation can be transformed in the following way, so that we are able to describe shear flow as a sequence of many infinitesimal strains. We would say a little step strain, delta gamma I, is introduced at a finite rate, finite shear rate, over a small time interval delta t. So this is an incremental strain introduced, and we would have now this equation here rewritten, saying the stress is given as the sum of all those incremental strains, and the strains would be gamma dot times delta t, weighted with the relaxation modulus. And since all those strains are small, we can rewrite this as a differential equation. We are just summing up all the strains from minus infinity to current time t, all the strains being gamma dot times delta t, and weighting it with g. And in this writing, t prime is just any time in the past, and t is the current time for which we would like to have the stress. Now, this is already the equation which we are going to use. It has been derived for the shear stress so far. We just looked at a relation between shear stress and shear strain. You might see that. Green is not the best color, I realize. So this is the equation which we derived. And if we would look at tensor components, we would have the shear stress covered and the shear rate being covered here. And we haven't talked about any other components of the stress tensor. Okay? But you can see that in the general format, where everything is linear, we would derive relations for each of the stress components. And the equation in its most general form is given by the stress at time t, equal to the integral from minus infinity to the current time t over the relaxation modulus times 2 times the rate of strain times dt prime. And this is the Boltzmann equation which we are going to use to describe all kinds of phenomena in linear viscoelasticity. Now, my focus, my interest in this is really in this modulus, the determination of this modulus. How can we get it? What's the typical behavior in various flows? And so we really want to look at the material. So we are interested in the relaxation modulus. And this modulus is now as a function of t minus t prime. Sometimes the time sometimes is plotted as s. That's just a distance into the past. So the relaxation modulus is a decaying function. In the liquid, the decaying function goes to 0, and in the solid, it will level off at some modulus, which is the modulus at long times, called the equilibrium modulus of this material. Special forms, mathematical forms of this function have been proposed. For instance, a single relaxation mode would be typical for the Maxwell fluid, where the relaxation modulus is just the exponential decay times a front factor. We can have a discrete spectrum of relaxation times where we have just a sum of those Maxwell modes describing the relaxation behavior, plus the equilibrium modulus. This would apply to a solid if this is finite, or to a liquid if this is equal to 0. The Maxwell fluid obviously is always a liquid, so I didn't have this component in there. And you could rewrite this equation in a continuous format, write the continuous spectrum, so the modulus is given as this type of function, and h of lambda would really be the fingerprint of the material. Now the questions are, What's the molecular origin of this h of lambda? And chemists have been very interested, and polymer physicists would write a model for the molecular motion and then derive this h of lambda from that. It turns out that the polymer physics actually is not concerned for h of lambda. They would derive something for the modulus itself. But the data, when we look at the data, you will see that h of lambda is adopting a very simple form under some conditions. So it's a worthwhile material function to look at. So we would like to know h of lambda for specific materials, depending on the molecular architecture, distribution of molecular sizes, blending rules, for instance. The molecular weight distribution has a very sensitive, very large effect on h of lambda. Chain stiffness would change h of lambda. So the fingerprint, the molecular fingerprint is visible in h of lambda. Ferry has a very nice description of all the different materials and their relaxation spectrum. So Ferry's book in, I think, second edition, 1980, would be a very good source to look up, to read up some of the material behavior. As a reminder, the Boltzmann equation is only valid at small strains. It is at large strains, the material behavior is nonlinear, and we have to do something more. So the limitation is really small strain, and this could be at high rates, low rates. There's no deviation. So it's valid there. And now, if the deformation rate is sufficiently small, so that the relaxation of the material is competing with the building up of stress in the system, then the memorized strain in the material is very small. And we can identify this now for the Boltzmann equation. We could say from this integral, which goes from -infinity to the current time t, everything in the past has been forgotten, is unimportant, except the most recent past. And I said if we take in t minus 5 times the longest relaxation time, then we should be on the safe side. Everything beyond that is forgotten. So if you replace this with this limit here on this side, and then calculate how much strain you get in during that interval from t minus 5 lambda max to t. What's the total strain in that? And if that total strain is small, then the memorized strain is small, and everything is following linear viscoelasticity. So that's why you can have experiments with infinitely large strains and still apply linear viscoelasticity, apply Boltzmann's equation, because the memorized strain is very, very small. Now, this is obvious. I think it's pretty straightforward. But I remember we had a discussion in the Society of Rheology in 1974 about the use of linear viscoelasticity in polymer processing. And many suggestions have been made about a correlation between linear viscoelastic properties and processing behavior. And it was also great confusion in the discussion. And then somebody got up and asked, can anybody define linear viscoelasticity? And that's what I'm just talking about, the definition of linear viscoelasticity. And there were, of course, a number of people in the audience who could have defined it very easily, but they somehow didn't get up. So nobody defined or could define linear viscoelasticity. Obviously, many who used the word linear viscoelasticity didn't know what it meant. So the discussion was stopped at that moment. The discussion was over. By the way, the person who asked this question is Arthur Lodge. He's famous for his good questions in cases like that. Okay. Okay, so now you know. Maybe I should ask it in the midterm. Ask what's the definition of linear viscoelasticity? Yeah. Yes. And now, very important. This equation, the Boltzmann equation, is not limited to specific flows. You can describe shear flows, extensional flows, all flows under the above conditions with that. So in that case, it is a general constitutive equation. When you talk about linear viscoelasticity, there's only one equation which describes everything. And the limiting case of that for the pure liquid, the liquid which has zero memory, would be the Newtonian liquid. And the limiting case of the perfect memory where no relaxation occurs at all, where G is a constant, that's the Hookean solid. So those cases are included in this case. And there's only one equation which really makes it easy. The jungle of constitutive equations starts with large strain behavior. The question is, how can you describe large deformations in shear and extension and all of this? So in linear viscoelasticity, from a phenomenological point, you have one equation. But we still would like to know which molecular motion or what model for the molecular motion gives the right value for the relaxation modulus. And that's where the different opinions come up in linear viscoelasticity. Now the equation of, as proposed by Boltzmann, has many different forms. So I would like to discuss a few alternative forms with you. So this would be the equation, which is general and complete in the sense. Let's introduce a strain as an integral over the rate of strain tensor. And we would use that strain now by this operation here, by our integration by parts of the Boltzmann equation. We would take this equation, we would integrate this part, we would differentiate this part. The front factor here is equal to 0 because at minus infinity, t minus infinity, the relaxation is perfect, so nothing this is equal to 0. And at the current instant, t prime equal to t, there's no strain introduced in the material, so this part, the strain tensor, is equal to 0. This E is equal to 0 at the current time t. So everything is left, which is left is this type. We have the derivative of the relaxation modulus, which is called the memory function. Now this is combined with a minus sign up front. So the memory function is minus the derivative of the relaxation modulus. And we can write the stress now as the memory function times the strain integrated over the past. And if you put in, say, a right strain tensor, a finger strain tensor here, then we are already able to describe some finite strains. And that actually would be the large rubber-like liquid. Yes, question?
What happens to that factor 2 in there? G times 2dt. Right. Yes, that's right.
That's right. Let's put maybe, I don't know. It's really up to you. I'm making up a strain measure to accommodate this. On the blackboard. Okay. How about this? Ah, that's nice. Okay, we keep the 2 with the rate of deformation tensor and just define a strain tensor like that. Okay, that I think that should be doing it. And then we keep the format down here. And you can use this equation whenever it's convenient. When you have the strain history, for instance, you use this equation, or when you have the rate of strain history, you use that equation for predicting viscoelastic behavior under all kinds of deformations. Now, very popular is also the differential model, and I wrote it down here for a single relaxation mode, the so-called Maxwell model, where the stress plus lambda times the rate of change of the stress is equal to the viscosity times the rate of deformation tensor. Now, this equation is exactly identical to the Boltzmann equation in the case of a single mode. So you would have one mode being used, and we will introduce an exponential function in this case. Now, you can derive the relation between the two by taking this equation here and taking the derivative with respect to time. Okay? Now, the time derivative of this integral requires the so-called Leibniz rule. You will take the integral of the top here times the kernel at the top minus the integral, minus the differential on the bottom, times the volume at the bottom, well, the differential on the bottom is equal to 0. And then you can move the differential inside this equation, and that's what I was doing. I put the differential inside, and then d dt is only working on this exponential function. And as you can see, that this reduces then to the rate of change of the stress tensor is equal to rate of deformation times this front factor minus the stress itself. You can express this with the stress. And rearrangement gives the stress being equal to the rate of change times lambda equal to eta times 2 times e. And that's equal to the Maxwell equation. That is equal to the Maxwell model on the top. And the last point I want to make here, actually in the handout I gave you the Leibniz formula if you want, in case you want to do this differential yourself. If we have now, that's the last point, if you want to have a set of relaxation modes here, not a single mode, then you would write down the Maxwell model here for each modes characterized with lambda I and gi, and then you would sum up the stress contributions of all those modes, and you would get the total stress, and that's completely equivalent to the Boltzmann equation which we had before, and would be the Boltzmann equation with a discrete spectrum. So with that, we have a complete definition of the linear viscoelastic behavior from a phenomenological point of view. We will do a few exercises, some calculations, predict some material functions with that equation, and compare to experimental evidence. And then we will talk about possibilities of measuring the relaxation modulus, measuring g of t and h of lambda. Thank you. That's everything for today.